Hi Sakshi, am I audible? Is my screen visible? Yeah. Can somebody please unmute themselves and confirm whether I'm audible?
Yes, sir.
Okay, thank you. Thank you for confirmation. So I welcome you again for this week 4 discussion. So today we will discuss about very important topic which is enzymes, and this is one of my favorite topic in biochemistry. You will see this in biochemistry. You will also face some of the problem in chemistry also, like in chemical kinetics, where you find the catalysis. The same role is played in the biochemistry by enzyme. So enzymes are nothing but protein, as you are aware about it. Okay. So now discussing about it, it takes me a kind of a very good uh, pleasure that enzyme. This topic is usually taken by most of the competitive examinations, such as you will find the questions from like in GATE examination or in CSIR-NET examination or DBT. You name any competitive exam, you will find one or two questions from enzyme kinetics. So pay attention to these lectures. From today onwards, the live interaction for enzyme will start. And in the next session, I will discuss about more on the enzyme mechanism, how the catalysis begins, and then what are the different amino acid residues involved in the enzyme catalysis. So these all things we will discuss at greater details in upcoming live interaction. But in this week 4, this is the basic introduction of enzyme and also the classification, then the models that represents the mathematical model or expressions that are there you need to study for the enzyme catalysis. So these all things we will discuss today in this live session. So I welcome you again. I'm Karan Kumar, Prime Minister's Fellow at IIT Guwahati. And for those who are joining through YouTube and who will be watching after the session, for them, this live interaction sessions are for. Hello, am I audible?
Yes, sir.
So, hello,
Yes, sir.
am I audible? Hello. Okay,
Yes, sir.
there was some internet disconnection from my side. So okay. So as I was talking about this course for the learners who are who will be watching the recording on YouTube. So for them, this course biochemistry is regarding the basic fundamental biochemistry course, which talks about from protein amino acid, the lower level of amino acid to applied biochemistry. So these sessions in this particular live interaction, the first thing will be as usual my introduction, then revision of the week 4 topics that you have come across, that you might have watched. Those who are enrolled in the course, they have already watched the revision. So we will take the topics what were there, and then scope of this topic with the research perspective. I will also discuss that, and the important key notes in that you can take from this topic or this live interaction, which might be useful for you in GATE Excel or CSIR-NET examination. So the important thing here is my website. To know more update about me, check out my website, and you can email always on my email ID. So now coming to the concepts that were covered in the week 4. So ma'am has discussed the nature of enzyme and enzyme classification. So you might have come across there are total 6 enzyme classification, and these enzymes are denoted by some kind of IP address where you will find that 3.4.1.1 classification. So for every enzyme, there is a enzyme ID. Okay. And these are determined by the Enzyme Classification Committee EC numbers. Okay. So there are total 6 enzyme classes based on the role they play and their functionality in the biological system. Then then next man had talked about active site and its catalytic efficiency, how to determine the catalytic efficiency of a particular enzyme, and what are the amino acid residue involved in the enzyme active site. Then she talked about the effect of parameters on catalytic activity of enzyme. So there are several parameters, process parameters, environmental parameters, and many more, which can affect the enzyme activity or its catalytic activity. Then she talked about the Maclaurin-Menten kinetics. This is a mathematical expression of representing a single substrate enzyme complex system in which you will find one substrate, one enzyme, and one product. So those are represented more formally by Maclaurin-Menten kinetics. And ma'am discussed about the features of Maclaurin-Menten kinetics, then linear Lineweaver-Burk plot, Etzi-Hofstee plot. Then she also touched upon bi-substrate reactions. In bi-substrate reactions, you will have more than one substrate, and particularly while enzyme will be taking two substrates and then it will be releasing two products. So based on that, ma'am also discussed the mathematical model for bi-substrate reactions. There are two models, which are the simpler one, which is ping pong by and ordered by. Then active site of the enzyme specificity, lock and key mechanism, and induced fit mechanism to represent how enzymes take the substrate and then they process it, and finally you get the product out of this enzyme catalysis. So few general questions that I would like to ask. One of them is, what do you understand by the term enzyme catalysis and its efficiency? So is there again a network interruption? Okay, sorry about that. Again, there was a not network interruption from my side. So I don't know why this problem is persisting from yesterday itself. So no problem. We will again move ahead. So the first question that I would like to ask, what do you understand by the term enzyme catalysis and its efficiency? You have gone through the module 4 and you have completed both lectures, lecture number 7 and lecture number 8. So in that, can somebody brief me what is enzyme catalysis? What do you understand by it? Anyone can unmute themselves and answer this question. Any idea what is enzyme catalysis and what is its efficiency? How to determine it? And why understanding the enzyme kinetics is so much important in biochemistry? Why do you need to understand enzyme kinetics? Anyone want to try? Don't be shy. You can answer anything. There is no obligation that your answer should be right or wrong. You can answer anything. You must interact. That is the only thing that is required from this live interaction. Hmm. Okay. So enzyme catalysis, as the term, if you dissociate these terms, first one is enzyme, another is catalysis. So why catalysis? catalysis is important because you need when a particular reaction, let us say there is a lipase, there is a esterification reaction. What is esterification reaction? Esterification reaction is nothing but that alcohol ROH plus carboxylic acid, it will give you RCOR and water, right? When this reaction is happening, one alcohol and carboxylic acid molecules are reacting and they produce ester molecule and water as a byproduct. This particular reaction is very much slow in absence of the enzyme. The enzyme as in lipase. Lipase is one of the six category member of six category enzyme classification. So all the enzymes, whatever you will hear, whether it is pepsin, whether it is lipase, whether it is chymotrypsin, or any enzyme, whatever you think of, all enzymes are the family of uh, either of these six classification. So lipase is one of those member, and this lipase particular this enzyme catalyze the esterification reaction. It also catalyze the hydrolysis, which is the reverse of esterification, then transesterification, and many more reactions. So in absence of lipase, this reaction is very slow. But when lipase is there, then to attain the ester product is much more easy, and it produces the ester much faster in presence of lipase. So how this process is happening? This process is happening due to the presence of lipase, which is enzyme. Okay. Now catalysis means this lipase will act as a catalyst. What is catalyst? Catalyst is, you can understand the catalyst term by one thought experiment. Let us say you want to go from A destination A to destination B. There are multiple routes to go from A to B, but there will be only one path which will be the shortest, right? And this is the shortest path. Now there will be some different path going from here, and then from A to B there are multiple paths. Let us assume this is first path, this is second path, this is third path. Now if any person from if any person is moving from A to B, they can take any of the path. Okay, but if let us assume there is somebody, a guide, who is telling you if you take this particular path, it will be the shortest path. Then if you go through path number one, then you will reach to your destination much earlier than the other two paths. This is what the enzymes plays a role. This is where the enzyme play a role. And you can understand enzyme as a guide. So if enzyme is there, let us say guide is there. So if guide is like if a person is guiding you, you go from A to B via path number one, does it take anything from guide, like whether the guide will be consumed or he will be exhausted or something? No, right? It is only guiding you from A to B. That is what the lipase or enzymes also do. They don't get consumed during the reaction. They might be modified in between, but at the end of reaction, it will be recovered completely from it. Okay. But in absence of guide, if you take 2 and 3, these paths will be longer and it will take much more time than the path number 1. So thereby enzyme catalysis is important because they reduce they particular kind of reduce the time of reaction to process, or because all the chemicals reactions that happens in our body or in any biological system or in industry. So in all kind of system, if catalyst is present, then the reaction will achieve its destination much more faster than the other route. Okay, so this is how the catalysis is important. Now, now what is mean by efficiency? Now there are two guides. Now think there are two guides. Guide number G1 and guide number G2. He is talking in English and he is talking in Hindi, and you understand Hindi much more than English. So both will guide you through this path. But the person who is guiding you in Hindi, you will understand much more than the person one. Person two will guide you much more effectively than person one, because you both have the common understanding of Hindi, and that will help you to attain your path much more easily. However, guide one who is talking in English, he will also guide you through the same process, but because you have little less understanding of English, so you will have difficulty to reach your destination much faster. So, and it will take time to understand that particular long language, right? So this is what the two enzymes also do. Like if there are two enzymes, E1 and E2, and this particular enzyme is more efficient in progressing this particular reaction much faster, then E1 will be having the much efficiency than E2, right? And this efficiency arises due to the specificity, because all enzymes, all or proteins, they have their unique features in their structure. Some features will be conservative throughout the organism, throughout the biological system. So those conservation is due to some particular amino acids that will that topic we will discuss on greater details in the upcoming live interaction session. So just to give you a brief analogy how efficiency arises in enzyme system, enzyme catalysis, because of the specificity of a particular enzyme to the substrate, they have like because of the efficiency, their efficiency increases, and this the measure of efficiency is is calculated by the expression kcat by km. Now what is kcat and km, that we will discuss in greater details in the upcoming slides, when we will discussing about the enzyme catalysis. Now you have understood about catalysis and efficiency. Is it clear to everyone, or any doubt? What is catalysis? What is efficiency? Have you understood? Uh, Nobody is talking. Has everyone understood this?
Yes, sir.
Okay. Thank you for confirmation. Now, same thing goes to the kinetics. Now, what do you mean by kinetics? Kinetics is important because to understand that particular system, whether this how like now you know that lipase catalyze the reaction or esterification reaction. Esterification reaction is catalyzed by lipase. Now you understand this fact. Now after that, how this reaction will, how much reaction this will be faster than other things, and what is the mechanism of the catalysis going inside the depth, you need to understand the enzyme kinetics. Kinetics means how faster or how slower. It involves the term of time in this particular terminology. So when that like how faster, how much slower, and what time it will take, then what will be the enzyme quantity required, what will be the influence of other substrates. When you understand all these facts, all these concepts, that becomes the whole enzyme kinetics. Enzyme kinetics deals with the different mathematical expressions, different mathematical model to model the enzyme catalyzed reactions. Okay, what is the scope of the topic with research perspective, that I will discuss in greater details in the upcoming slides. And we will also talk about what are the type of questions asked in the GATE and CSIR-NET examination from this topic. Now, before that, I would like to ask few of the questions from the slides that ma'am has discussed. So, which of the following best describes the assumption made in steady state kinetic analysis? The concentration of substrate is decreasing. The concentration of enzyme substrate complex is constant. The total amount of enzyme decreases. So, which of this statement is best describing the assumptions made in steady state kinetics? Okay. So, your options are only statement 1. Option B is statement 1 and 2. Option C is statement 2. And option D is statement 3.
1 and 2. Option 1 and 2. That's B option.
Option 1 and 2.
Yes, sir.
Okay. Any
Option
other?
C. Option C.
Option.
Only
Okay.
second one.
Any other? So one for option 1, or one for option 2, or one for this. And anyone else? What do you understand by steady state? Can somebody explain? What is steady state?
Acetate where the amount of product formed will be equal to the reactant present.
Okay. Okay, very good. And in like simpler term, in simpler term, steady state represents where the concentration does not change, right? Or by definition, if you say steady state is the time of progress of reaction where the there is no change in concentration of the enzyme substrate complex. Okay, so at that state, the and at that state, your concentration of the reactants products, or there will be no change in the concentration of any reactants or product, and that change is represented by DE by DEA, DES by DT, means this is the rate. So rate will be equal to 0. So if rate is equal to 0, that doesn't mean the ES concentration will be 0. That means the ES concentration will not change. That means it will be constant. So, and that holds true for all the reactants or product. Okay, that is the steady state kinetic assumption. The first statement, which is the concentration of S is decreasing, this this violates this particular assumptions, because there will be no change in the concentration at a steady state. So if it is decreasing, that means this statement is wrong. Now, in the part 3 also, like it is telling about the total amount of enzyme decreases. So enzyme amount will also not decrease, right? Anyhow, enzyme is not being consumed, so this statement is anyways wrong. Okay. Now the only statement which talks about the steady state, that means the ES is constant. So option C is correct here. Is it clear? Okay. So option C is correct, which means the concentration of ES will be constant. Now the next question is the number of substrate molecules converted to the product in a given unit of time by a single enzyme molecule at saturation is referred to as option A dissociation constant, option B half saturation constant, option C Michaelis-Menten number, option D turnover number. The number of substrate molecules converted to the product in a given unit of time. What is this particular thing known as? Any idea?
Turnover number.
Turnover number. Any other option? Turnover number is the correct answer. Here, the number, this is by definition, turnover number is termed as that you have a particular, like you have substrate. What is enzyme substrate complex? Like reaction E plus S, it will be in the equilibrium with enzyme substrate complex, and rapidly it will give you enzyme plus product. Okay, so turnover number is known as the number of substrate molecules that this particular enzyme is converting the number of substrate molecules to the product in 1 unit of time. That particular term is represented by the turnover number. Now the next question is, in an experiment, at which wavelength the absorbance is measured for the sample protein BSA? Now, can somebody tell me at which wavelength the sample protein will absorb UV light?
Sir, 280 nanometers.
280 nanometers, very good. Why it absorbs at 280 nanometer? Why a particular protein absorbs light at 280 nanometer? Due to the presence of
Aromatic ring.
tryptophan. Yeah, aromatic ring. Due to the presence of the pi aromatic ring, and that is present in the tryptophan, tyrosine, and phenylalanine. So because of that, because BSA also contains tryptophan moiety, and this tryptophan is able to absorb UV light at 280 nanometer. Now, coming to the next question, the class of enzyme that catalyzes synthetic reactions where two molecules are joined together and ATP is used. You are joining two molecules. You are joining two molecules, and then you are yeah, you are joining two molecules and you are utilizing ATP. So which enzyme will do this? Hydrolysis, ligase, or isomerase?
Ligase.
Ligase. Very good. What are the role of other three enzyme? Isomerase does. What does isomerase function?
Isomerization reaction.
Isomerization reaction. Very good. Ligase.
Breakdown. Breakdown of substrate.
Sorry.
Breakdown of substrate, I guess.
Breakdown of substrate.
Yeah. I'm not sure about lyase.
Okay. Anybody else? What is the role of ligase?
Add water or carbon dioxide across double bond.
Yeah. Add atoms or molecule group of atoms across the double bond, unsaturation. What is the role of hydrolyze? Hydrolyze? What is the role of hydrolyze?
Breakdown of carbohydrate with the help of water. Addition of water. Or
Only
uh,
carbohydrate.
no, any other substrate as well.
Okay. Anybody else want to give their opinion on hydrolyze? What is the role of hydrolyze? Okay, you were correct. Now the next question is, forward. Not able to move the slides. It is not. Wait. Somehow my slides are stuck.
So it is displaying below.
Yeah.
I think.
Annotation started and then it got some problem. So is it okay now? Yeah. Are you able to see the slides?
Yes, sir.
Movie. Yeah. Okay. So the next question is: a student conducts an experiment to test the efficiency of certain enzyme, which would be probably not the results of charge in the efficiency of enzyme. Your statements are adding more substrate but not enzyme, carrying out the experiment in absence of water, and adding an acidic solutions to the reaction mixture setup. Options are only one changes the enzyme efficiency. Option B, 1 and 3 changes the enzyme efficiency. Option C, only 2 changes the enzyme efficiency. And option D, 1, 2, 3 changes the enzyme efficiency. Now, before answering the question, analyze these three different scenario in which scenario does affect the enzyme efficiency. Okay. Yeah. Answer. Try this question. A student is testing the efficiency of enzyme. Okay. So which would not probably result into the charge, which would probably not result in the charge in the efficiency of the enzyme. So here the question is not result in the charge in the efficiency of enzyme. Adding more substrate but not enzyme, carrying out the experiment in absence of water, and adding an acidic solution to the reaction mixture setup.
Sir, is it charge in the efficiency or change in the efficiency of enzyme?
I think it is change. Wait. This question was taken from the shared assignment only. Let me check. Change in the efficiency, sorry. This is change in the efficiency. Yeah. Okay. What would not result in the change in the efficiency of enzyme? And please give the rationale behind your answer. Why are you thinking like that? So anyone? Give me the fate. If you are adding more substrate but not enzyme, what will happen?
So I think efficiency will not change with the addition of substrate because the enzyme will continue to make the product whatever substrate it has available. the addition of more substrate will not change anything, because enzyme will be only able to convert that much of amount of substrate which it will. If I have made my point clearly.
Okay, okay. Any other opinion that I can have on the adding more substrate but not enzyme? Will it affect the enzyme efficiency?
So
Any
it
other
may affect,
opinion?
because if we have a lot of amount of substrate and not
Yes,
sufficient enzyme, then
yes.
then the reaction may not be completed as sufficiently.
Okay. So there are two contradictory opinions. Okay. Any other opinions I can have?
Sir,
So
I
one,
think
yes, you think whether it will affect or not affect?
it affects, sir, because particular substrate has particular enzymes. So there is no formation of ES complex and there is no product formation.
There is no product formation. Okay. So you are saying that before it was catalyzing, if you add more and more substrate, it will not even catalyze the reaction, or will it catalyze?
Not catalyzed, sir.
Okay. What about the second statement? Carrying out the experiment in absence of water. If water is not present there, like let us say in the your reaction system, you had initially water molecules, but at like you remove the water and then you are carrying out the experiment. Will it affect the enzyme efficiency?
So I think it will affect the efficiency of enzyme, because certain enzymes require water to catalyze its reaction.
Okay. Any other opinion? So all are in favor of that it will affect the enzyme catalysis.
Yes, sir.
Okay. So yes. Now the third statement, adding an acidic solution to the reaction mixture setup. Will it affect the enzyme catalysis, enzyme efficiency?
Yes, because adding the acid will denaturate the enzyme, which is a protein itself.
It will
So
denature the denature.
enzyme, it will denaturate the enzyme, I'm saying.
Okay, it will denaturate the enzyme. Okay,
Yeah.
why it will denature? Let us say if a certain
Because
enzyme is more functional in the acidic environment, then what will be the main cause of adding? If you are adding the solution, what will it impart on a particular enzyme? What will be the fate of enzyme in the more acidic solution? Let us say you are not adding like highly concentrated acid. You are adding some amount of acid. Then will it change the efficiency of enzyme?
depends if that enzyme will be denatured at that pH.
Okay, okay. So it will affect, right?
Yes, I guess.
Yes, sir, it affects because every enzyme has its optimum pH. So
Yeah. Okay. So adding the acidic solution, it will lower down the pH, right? Or it will
yes,
increase the
sir.
pH.
Lower down.
It will lower down the pH.
Yes, sir.
Okay, fine. So now what will be the option? What will be the answer among all four? Option one, option B, or option A, option B, option C, or option D?
I
What
think
is your take?
option D because all changes enzyme efficiency.
Yeah, actually that is was the case because all the enzymes they have the optimum pH. So if you are adding a solution, it will increase. It will either like if in case of acid, if you added base, then also the reaction system might have disturbed because all enzymes operate at its optimum pH. It will operate at different pH also, but the efficiency will not as much as when it will be on its optimum pH. So adding to the acidic solution, that does not mean the enzyme will be denatured, but the change in pH that causes the loss of enzyme efficiency. Okay, so yes, it will affect. Now you have correctly answered that carrying out the experiment in absence of water. In absence of water, when solvent is not there, it will affect the enzyme reaction system. If initially it was optimum for the if water is optimum for the enzyme catalysis, then removing the water will impact its catalysis. Now adding more substrate but not enzyme. Let us assume now let us discuss the Michaelis-Menten kinetics. In Michaelis-Menten kinetics, to give you more clear idea about it, in Michaelis-Menten kinetics, if substrate concentration is much more than Km, then what will be the scenario? If substrate enzyme, if in enzyme substrate reaction, if substrate is much more than Km, that means the enzyme will operate independent of its like uh, then enzyme will operate independent of substrate concentration. That means it will operate at the its velocity maximum. The reaction velocity will be maximum. Now, if substrate concentration is that, these are the assumptions of Michaelis-Menten kinetics. Now, if substrate concentration is much less than the Km, then at that scenario, substrate velocity, initial velocity of the reaction will be directly proportional to the substrate concentration. Okay, and this is what you see in the Michaelis-Menten plot also. In Michaelis-Menten plot, on the y-axis you have velocity of the reaction, and on the y-axis and in the x-axis you have substrate concentration. That is what you also notice, that initially it follows the first order kinetics, which is representing why the substrate concentration is much less than the Km. At that it will follow the first order kinetics, but when the substrate concentration is much bigger than the Km, then it will not depend on the substrate concentration at all, and the reaction will happen at its maximum efficiency. Okay, so this is your Vmax, and your Km is the half of its Vmax. So somewhere here. So at the lower concentration, lower than the Km, when the substrate concentration is lower than the Km, then it is first order kinetics, which means it is directly proportional to the substrate concentration. Increasing the substrate concentration will increase the velocity of reaction. But once it goes to the this direction, means at here the substrate concentration is much more than the Km. Here the substrate concentration. So here at the higher substrate concentration, it is independent of substrate concentration. The velocity of the reaction or efficiency or the rate of the reaction is independent of the substrate concentration, and it follows a zeroth order kinetics. Okay, so here the velocity of the reaction is Vmax. So thereby adding more substrate will affect the enzyme. Adding more substrate will affect the enzyme efficiency. So all three will change the enzyme efficiency. Option D is correct. Is it clear? Now coming to the next question. In a protein, when the tryptophan residue becomes hydrogen bonded or is exposed to the water, the emission shift to a longer wavelength. Is it true statement or false statement? This is related to the catalysis, because tryptophan may be here in the absorbance, like protein absorbs only when the tryptophan is present, like aromatic amino acid residues. The three amino acid residues, which are tryptophan, tyrosine, and phenylalanine, these are responsible for absorbance, for absorption of UV light or longer wavelength. So then the question is, when the tryptophan residue in a particular environment, if that is exposed to, if that is hydrogen bonded or exposed to the water, then will it shift the emission wavelength to the longer wavelength or not? let us say you have one absorption. You have one here. You have AU and absorption, and here you have wavelength of light. And without exposing, this particular protein is showing this kind of UV absorption spectra. Okay, but if that particular, let us say this is the enzyme, and here is the tryptophan residue. Right now it is in the buried in the pocket, like hydrophobic pocket. But when it is exposed to the water, but when this particular is exposed to the water and then hydrogen bonding is happening, what will happen to its emission spectra? Will it shift to the forward side or backward side? Any idea? It
So
will
it's
actually,
false statement. False.
it's false statement. Why?
So because yesterday we learned about when polarity increases, then bathochromic shift take place. Sorry, so when polarity increases, hypsochromic shift take place, and when polarity decreases, then bathochromic shift take place. Where hypsochromic shift represent decreasing wavelength, and the bathochromic shift showing increasing wavelength.
Okay.
Or when we add a tryptophan residue, which bond hydrogen bonded generally represent polarity, na?
Yes.
Sir, that means polarity increases, so wavelength will decrease.
Very good. It is a false statement. Okay. Now the next question is, enzyme X exhibit maximum activity at pH 6.9. Then this X shows a fairly sharp decrease in its activity when the pH goes much lower than the 6.4. One likely interpretation of this pH activity is that your options are the glutamine residues on the enzyme is involved in the catalytic reaction. A histidine residue on the enzyme is involved in the catalytic reaction. An enzyme is a metallic cofactor and the
Sir,
reaction relies
second,
on the, yes,
sir,
So
second
the
is not
slide is
correct.
slide is not visible.
Yeah, they are not correctly visible.
Is it visual now?
No, sir.
Okay, wait.
the previous one is visible, but the new one is not. Yes, sir. Now it's fine.
Okay, so you were here in this slide. Now is it visible? Is it visible?
Yes, sir. Yes,
Yeah.
sir.
So your question is the enzyme, there is an enzyme X that exhibits the maximum activity at pH 6.9. Okay. This X shows a fairly sharp decrease in its activity when the pH goes much lower than the 6.4. Then means if pH goes below 6.4, then there is a sharp decrease in the activity. One likely interpretation of this pH activity is that glutamic acid residues on the enzyme is involved in the catalytic reaction, or histidine residue at the enzyme activity is involved in the catalytic reaction, or enzyme has a metallic cofactor, or reaction relies on the specific acid-base catalysis. Which statement is correct? Which statement is more apt?
Sir, I believe option B is correct. Histidine
Option B
residue.
is correct.
Yes, sir.
So why histidine residue?
So histidine residue is a basic amino acid. So keeping it in more acidic environment will ionize it. So that way it may affect the efficiency or activity of the enzyme.
Okay. Yeah, you are very accurate actually. Histidine amino acid residue, you cannot term this as a basic amino acid residue because the nature, that is what the beauty of histidine residue. Histidine residue is a very special kind of amino acid residue that is more prevalent in, like, it is always found in the activity site, catalytic site of all the enzymes. Why? Because this histidine residue, the pK value of histidine is around 6. pK value is 6. Okay, so that means the pi value of histidine is 6. That means it is close to the physiological pH 7, which is 7.4. Because of this nature, when when the histidine is close to the acidic positive acidic environment, it will exhibit the positive charge on its surface. It will change its surface accordingly, and if it is in the acidic environment, it will change to the negatively charged amino acid, negative charge. Okay. No, I guess I have miscommunicated here. When the histidine amino acid residue, this amino acid residue is surrounded by the negatively charged amino acid residue, then at this, the pK value will shift to the rightwards on the basic condition. And if this particular amino acid residue, and it will contain positive charge, and if it is surrounded by the positive charge amino acid residue, then it will contain negative charge and it will act as a base. However, in this case, it will act as an acid. So the speciality of histidine that it can like travel forth and back, and that is why it is it is almost found in all kind of enzymatic enzyme catalytic site. Okay, because here the pH is showing that it is at the 6.9 and it is close to physiological pH, which is only possible in case of histidine. So if the pH is goes much lower than the 6.4 and there is a sharp decrease in its activity, it 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 is likely interpreted that the histidine residue is involved in the enzyme catalytic reaction. Okay. Now the next question is, in a Lineweaver work plot, work plot, which of the following effects affects the competitive non-competitive inhibitors? Okay, your options are: it moves entire curve to the right. Like, these are the 4 statements that might be true or not, and you have to find out the option. Statement 1 is it moves the entire curve to the right. Option 2, it moves the entire curve to the left. Option statement 3, it changes the y-intercept. Option 4, it has no effect on the slope. Your options are only 1 is correct. 1 and 2, 1 and 3, 2 and 3 is correct. Then 3 and 4 are correct, and only 3 are correct. Only 3 is correct. So which one do you think is true in case of Lineweaver work plot? If a non-competitive inhibitor is present, then what effect it will show on the Lineweaver work plot? Any idea? Any answer you have? Okay. Has ma'am discussed competitive inhibition, non-competitive inhibition in her lecture? In lecture number 8, has she discussed? Okay.
Yes, ma'am has given a brief description about Lineweaver work plot, but there is confusion regarding it.
Okay. Okay. Inhibition pattern has she discussed? In presence of inhibitor, what will be the fate of the plots and how it will react? So otherwise, I will give a brief about
No,
the inhibitions, enzyme inhibition.
no, she
Sir,
gave
please proceed.
Okay, okay. Then I will give a brief about it. Let me give you a new slide. So let us say there are three type of inhibition possible. So your enzyme substrate reaction is this enzyme substrate. Then it will form a enzyme substrate complex, and you will finally get enzyme and product. Okay. So during this process, let us assume that your active site of the enzyme is something like this. Like your substrate will fit into this. So that means your substrate shape should be like this. What if this is your substrate? What if there is another kind of compound which also has the same phase? Okay, let me change the pen color. Let us say you have a another substrate which also has the same phase. Now this will also can bind. This can also bind to the this particular site, right? Okay, so if in instead of substrate, if a particular compound, if another compound comes and binds to the active site, that means the substrate now is not able to bind to this active site. Thereby, you won't get your desired product. So this is what the inhibition is. Inhibition means either your enzyme is completely blocked or it is partially blocked, which is and its active site is not available for the its specific substrate to bind to its active site. So based on this inhibition pattern, there are three kind of inhibition possible. Okay, first is competitive inhibition. Then you can have uncompetitive inhibition and non-competitive inhibition. Now what happens in competitive inhibition? In competitive inhibition, let us say your enzyme is this and your substrate is this S, your inhibitor is this one. This is your inhibitor. Now, in competitive inhibition, both the substrate and inhibitor will fight for the same site. Okay. And if this particular fashion is happening, that means the inhibition is happening at this scale. Okay. So it will result you enzyme inhibitor complex, and your substrate will not be able to bind with the enzyme, and you won't get the product. This pathway will be blocked. Okay, this is competitive inhibition. Now what happens in like uncompetitive pure non-competitive inhibition? In that sense, the inhibitor will not bind to the enzyme directly. It will bind to the another site. Okay, in uncompetitive inhibition, in non-competitive inhibition, there will be some other site where inhibitor is coming and bind, due to which its shape, the active site shape is changed, and due to which the substrate cannot bind to its active site, and thereby the catalysis cannot happen. Okay, so this phenomena is known as the uncompetitive inhibition or non-competitive inhibition. Okay. Am I audible?
Yes, sir.
Hello. Yeah. Am I audible now? Yeah, there was
Yes, sir.
again network issue.
Yes, sir, you
There
are
was
audible.
again network issue. So as I was discussing the different type of inhibition, first one was competitive. Then another one was non-competitive. And then uncompetitive. Other than that, there are few more such as allosteric inhibition and others. So we will not go much detail into that, but we will discuss these three type of inhibition. So in the inhibition pattern, if there is competitive inhibition, then enzyme and substrate complex, then enzyme and substrate complex will be inhibited at the enzyme level itself, and you will get EI, due to which the enzyme product cannot be attained, and enzyme substrate, there will be competitive inhibition between the substrate and inhibition. So this is your competitive inhibition. However, in case of uncompetitive inhibition, what happens? In case of uncompetitive inhibition, your substrate, your inhibitor, hello, okay, yeah. So in case of non-competitive inhibition, what will happen? Your inhibitor will not bind to the enzyme directly, but it will bind to the enzyme substrate complex, and thereby it will make enzyme substrate inhibitor complex, and the reaction will not progress further, and it will form enzyme substrate inhibitor complex. So this is your non-competitive inhibition. However, in case of uncompetitive inhibition, both can follow. Either it can bind to the enzyme directly at enzyme, or it can bind to the enzyme substrate complex. So the if it is binding to the both side, then it is called as the uncompetitive. As the term represents non-competitive, non-competitive means your it is not competing with the substrate, but it is binding to the enzyme substrate complex. But in case of uncompetitive, it can bind to the both side, either on ES side or on the enzyme directly. Okay, thereby it is forming the EI complex and ESI complex. So in absence of inhibitor, your reaction, like your Michaelis-Menten kinetics is V naught is equal to Vmax into S by Km plus S. So if you reverse this equation, you will find what you will find. You will find the Lineweaver work plot, which is also called double reciprocal plot. Okay, and thereby you will get the Km by Vmax into ES plus S divided by Vmx into S. S is cancelled, and thereby you get the equation 1 by V naught is equal to Km by Vmax into 1 by substrate plus 1 by Vmax. Okay, so this is what Lineweaver book plot is. Okay, but in case of inhibitor, now let us assume the case of like competitive inhibitor. So in case of competitive inhibitor, your inhibitor is binding at the site where your like where your enzyme alone is present. In case of competitive inhibitor, so thereby it is affecting the formation of enzyme substrate complex itself. Okay, so thereby your equation will become 1 by V naught is equal to alpha Km, okay, alpha Km by Vmax by S plus 1 by Vmax. This is equation of uncompetitive inhibitor. Oh, sorry, competitive inhibitor. In competitive inhibitor, because it is affecting the K1, K minus 1, K2 all. Km is what? Km is minus K1 plus K2 by K1, right? This is your Km. Now, if Ki is coming into the play, it is again the substrate is being consumed due to this Ki value, and thereby your Km will be reduced, and it will affect, in competitive case, it will affect both Km and both Km and Vmax. Okay, so what is Km and Vmax? In Lineweaver plot, Lineweaver plot is double reciprocal plot, where it is the plotting of 1 by V naught initial velocity divided by 1 by S. It is the plot between 1 by S and 1 by V naught. So y is equal to mx plus c. Now your slope is mx km by Vmax, and you have an intercept of 1 by Vmax, right? So you have y-intercept at 1 by Vmax, and your slope is km by Vmax. Now, due to the inhibitor, your slope is changing. Your slope will change, but it will not affect the 1 by Vmax part. So your x-intercept will not change, your y-intercept will not change, but your slope will change, either in the positive direction or negative direction. That depends on the strength of inhibitor. Okay, so in case of competitive inhibitor, you are getting a slope change in slope. However, in case of non-competitive inhibitor, now let us assume the non-competitive inhibitor. So non-competitive inhibitor is acting at the enzyme substrate level, enzyme substrate complex level. So here you are facing the inhibitor, and it will form you enzyme substrate inhibitor complex, right? So thereby your Lineweaver work plot will become 1 by V is equal to alpha Km by Vmax into 1 by S plus alpha by Vmax. So what do you see here? You see your inhibitor is affecting both your slope and your intercept, y-intercept. Okay, this is the case of pure non-competitive. Okay, this is the case of pure non-competitive. However, in case of uncompetitive, it can bind on the both side. So your Lineweaver work plot will become 1 by V is equal to Km by Vmax into 1 by S plus alpha dash by Vmax. So it is changing only the intercept. It is changing the intercept, but it is not changing the slope. So if you are plotting these equations, so in case of like competitive inhibition, your intercept will not change. Your intercept will not change. That means your slope will change. So slope will change means it is passing through the same line. Your slope is changing. Your slope is changing. This is your without inhibitor. Without inhibitor. This is with inhibitor. Inhibitor 1 and inhibitor 2. This is your Lineweaver work plot 1 by V naught. Y 1 by S naught. And this is case of competitive. Okay. Now in case of uncompetitive, non-competitive, In case of non-competitive, both your slope and your intercept both are changing. So what you will see in this is without inhibition, your slope will change like this. Your like this pattern will also changing I1. This is I2. Your intercept is also changing and your slope is also changing. Right? Both Km by Vmax is changing and uh, your intercept. This is Y intercept. This is also changing. But in case of competitive, intercept is same, but your slope is changing. So this is the case of non-competitive. However, in case of uncompetitive, only your intercept is changing and your slope is fixed. So if your slope is fixed and your intercept is changing, that means these will be the parallel lines. Right? This is without. This is your I1. This is your I2. This is the case of uncompetitive. Is it clear now? You remember these three equations. You remember these three equations? So now interpret this question. Your question was, in Lineweaver work plot, the non-competitive inhibitor shows which of the following effect? It moves the entire curve to the right. Is it happening? Is it happening? Your non-competitive inhibitor was so only changing the, it was changing both slope and your intercept, right? It was changing the slope and then it was also changing the intercept. Right? Is it moving the entire curve to the right? This option is wrong. It moves the entire curve to the left. This option is also wrong. It is not moving the curve, but it is changing the slope and intercept. It changes the intercept and it has no effect on the slope. Sorry, non-competitive inhibitor. So the option, which option will be correct? Which option will be correct? Both 3 and 4th. Let me again cross verify.
Sir, did we confuse it with uncompetitive and non-competitive inhibition?
Yeah. I think. Let me again cross verify it. What did I tell you? That in case of non-competitive, the inhibition will occur. Inhibition will occur at the both side, right?
Yes.
In case of non-competitive, it can occur at the both side, but in case of uncompetitive, it okay. I confused actually. I confused you people. Let me again explain. This case was the uncompetitive. Okay, let me add one more slide and then I will clear this doubt once and for all. In case of competitive thing is fixed. It is acting at the directly enzyme site. Okay, due to which you get the enzyme inhibitor complex. And your equation, Lineweaver equation will be 1 by V is equal to 1 by V is equal to Km by Vmax. Okay, Km by Vmax into S beta A plus 1 by Vmax. And it only changes the slope. Your intercept will be same. So this is your competitive. Okay, this is your competitive. But in case of non-competitive, In case of non-competitive, it can act as the both side. I kind of confused you people that sorry, this is ES. And you are getting EP. So in case of non-competitive, it can act at both sides. Here also it can act. So you will get ESI complex and you will get EI complex. So in that case, it will only change it will only change the intercept. It will only change the intercept, and thereby you will get the Vmax apparent will be decreased. Okay. So in case of non-competitive, you will get the slope like this. Okay. This is alpha Km. Okay. Your intercept will change, but your slope, it will not have effect on the slope. In case of uncompetitive, you will get the parallel lines. Okay. So your correct answer will be here. So your correct answer will be option 3. Let me cross verify the question itself. What was the question? Non-competitive. Is it clear now?
So
Yes.
yeah, it's clear. I think if you will correct me, I think while drawing the graph for the non-competitive inhibitor, aren't you making the slope different for different line? I believe
Yes, yes.
you are misconfusing with the non-competitive and uncompetitive.
Uncompetitive. Yes, yes, yes,
Slope.
yes. Yes, yes, yes. In
Otherwise,
uncompetitive inhibitor, slope will be fixed. In uncompetitive inhibitor, your slope will be fixed. But in case of non-competitive inhibitor, your slope will change, but intercept will be the same. Y-intercept will change, but this intercept, x-intercept will be same. Your y-intercept will change and slope will be same. It has no effect on the slope. Your option C is correct here. Okay. Is it clear?
yes, sir.
But in case of uncompetitive, you will get the parallel lines. Okay. Your slope will be same. Your intercept, y-intercept will change. In case of uncompetitive. Now the next question. A small molecule that decreases the activity of an enzyme by binding to its site other than the catalytic site is termed as option A, allostatic inhibitor, option B, alternative inhibitor, option C, competitive inhibitor, option D, stereostatic agent. A small molecule that decreases the activity of an enzyme binding to the site other than the catalytic site.
Allosteric inhibition.
Allosteric inhibition, very good. Allosteric inhibition is that kind of inhibition where it does not bind directly to the catalytic site, but it binds to the other side. Because in the enzyme, there are multiple cavities. There might be the multiple cavity. So if a particular compound bind to the another site which is not the catalytic site, it changes the uh, shape of this particular catalytic site, because there will be an interaction at this site which may have the constraint on this particular cavity, and that changes the shape of this cavity, and now the substrate no longer can bind to this particular site. This inhibitor is called as the allosteric inhibitor. Okay. Now the next question, the double reciprocal plot from the Michaelis-Menten, which is also known as the Lineweaver plot, is given by this. To determine the Km from the double reciprocal plot, you would multiply the reciprocal of x-axis intercept by -1, or multiply the reciprocal of y-axis intercept on -1. Take the reciprocal of y-axis intercept, or take the x-axis intercept where V0 is equal to half of Vmax. How you will get the Km from double reciprocal plot? This equation is given here. Any idea? I will also give you the plot. Your y-intercept is 1 by Vmax. Your slope is Km by Vmax. This is 1 by Vmax. And here on the y-axis you have 1 by V0. On the x-axis you have 1 by S. Okay. So how you will get Km value from this plot? Any idea? Anyone? If this is 1 by Vmax, what will be the x-intercept of this? At the x-intercept, your 1 by V0 will be 0. Okay. Now calculate the x-intercept. X-intercept where your in the double reciprocal plot 1 by S, your 1 by V0 is equal to 0. In that case, Km by Vmax into 1 by S is equal to -1 by Vmax. Okay, Vmax cancel. So to get S, you will need what you will need? You will need -1 by Vmax. So if you multiply this, the reciprocal of x-axis, so at the x-axis you will have -1 by Km. Right. So if you multiply the x-axis intercept by -1, you will get reciprocal. You will multiply the reciprocal of x-axis. X-axis intercept is -1 by Km, right? So if you multiply this by the reciprocal of -1, then you will get the Km value. Right. Your option A is correct here. Understood? Or is there any confusion? Everyone understood? Hello. Am I audible? Hello.
Yes, sir. It's clear.
Yeah, is it clear?
Yes,
How
sir.
to get the Km from Lineweaver plot? Okay.
Yes, sir.
Now the next question is, a certain enzyme will hydrolyze egg white but not starch. A certain enzyme will hydrolyze egg white but not starch. Which statement best explain this observation? Option A, starch molecule are too large to be hydrolyzed. Option B, enzyme might enzyme molecules are specific in their action? Option C, egg white act as a coenzyme for hydrolysis. Option D, starch is not composed of amino acid. What will be your observation? Observation that a certain enzyme will hydrolyze egg white but not starch. This is a very basic concept in enzyme kinetics or enzyme.
Sir, option
Option
B.
B.
Option B.
Yes,
Why
sir.
do you think?
Yes.
Because every enzyme is
That
specific
enzyme
from.
have a specific site for a specific substrate.
Yes.
That's one.
Yeah. So option B is correct here. Because enzymes are specific to their substrate. That is why the enzyme that is hydrolyzing egg white will not hydrolyze starch. For hydrolyzing starch, there will be another enzyme, which are the enzymes that hydrolyzes starch and other carbohydrates. Okay. Now the next question, based on the requirement of activation energy, enzymes can be defined as those which do not require activation energy, which lowers the requirement of activation energy, which increases the requirement of activation energy, and which do not change the requirement of activation energy.
Lower the requirement of activation energy.
And how does they do it? How does they do it? Lowers down the requirement of activation energy.
They act as catalyst. That's why.
Enzymes are catalyst. So that is the fact. But how they lowers down the activation energy. So first let me explain you in a good better way. This is a kind of energy, like this is an energy landscape that I had showed yesterday also. On the y-axis you will have free energy. On the x-axis you have progress time. Okay. Now you have a substrate here. This is your substrate, and as always, product will be lower in energy of substrate, lower than the substrate. Other than if it is not true, then the reaction will not progress, right? Product should have the energy lower than the substrate, and in between it will take a leap. Okay, where it will, before going to the product, it will form a transition state, TS1. Transition state can be like you can have multiple transition state also before going to the product, but let us assume only one transition state is here. Okay, so the energy which is required from this state, from this the difference between the substrate energy level, this will be the one energy level, and this is the another energy level. The difference between these two energy levels are known as the activation energy, EA. Now this path, like now, as I have in the beginning I told you that you are going from A to B using three different paths. One was something like this complex, one was straight, and one was something very much complex. So path 1, path 2, path 3. Now if it is going, let us assume it is having one transition state and going to the product. Now what enzyme will do? Enzyme will not change the substrate, it will not change the product, it will give the product and substrate as usual it was giving without enzyme. But what it will change, it will guide the substrate that you go to the shorter path and reach to your product level. And how does they do it? They do this by giving a proximity of substrate collision. Okay, because they have kind of, if you study So this is a particular substrate binding site, and there will be one product binding site. Now there are different amino acid residue are there in this pocket, these two pockets. Now at that transition, what will happen? Because there are as you might have studied in chemical kinetics, before a product need to form, you should have a fruitful collision between the reactants. If there are two reactants, let us assume there are two reactants, alcohol ROH and RCOOH. These two need to be collide effectively to produce ester. So if you have a box where there are lot of, this is a chemical reaction system. Now red represents alcohol molecule and your blue represents carboxylic acid. Now it is randomly distributed in this reaction system. Now if there is fruitful collision between the two reactants, then only you will achieve the product. So in absence of enzyme, these these reactions, there might be some fruitful collision, there will be some collision which are not fruitful at all, and you will not get the product. Thereby the reaction will be slower. But in case of enzyme, if enzyme is there, let me represent the enzyme by different color. Okay, let us say you have an enzyme here in this system, and it has a site for both substrate. So what will happen, that these two substrate will bind to its active site, and this enzyme will bring the two reactants much closer, so that the reaction, this collision is fruitful in much of the cases, more of the cases. Thereby it is reducing the path that one reactant, let us say this reactant want to collide with this one, then the enzyme will bring these two much closer, so that the reaction, the collision is fruitful, and thereby you get the product much easily, and the reaction is progressing faster. This is what is known as the lowering down the activation energy. Now the transition state, the only thing that is changing is the transition state. It is not, enzyme is not changing the product substrate, it is not changing the energy level of product, but it is changing the energy level of transition state by providing a sufficient vicinity, so that they collide much more fruitfully and much more easily. So this reduction accompanied by the lowering down of activation energy, and thereby it is providing the ample space. There how it is lowering down the requirement of activation energy. Is it clear? Now coming to the next question. Your next question is, for a reaction that can take place with or without the catalysis by enzyme, what would be the effect of enzyme on the system, on the different state? Or statement 1, standard free energy change of the reaction. Statement 2, activation energy of the reaction. What would be the effect of the enzyme on the activation energy of the reaction or initial velocity of the reaction? Options are: first, no change; second, decreases; third, initial velocity of the reaction increases. First, no change; second, increases; third, decreases. First decreases, second, no change; third, decreases, increases. First increases, second decreases, and there is no change in third. So which is the correct option?
So enzyme will have no change on the free energy chain. That it will have no effect on that. On the activation energy, it will decrease the activation energy, and it will increase the initial velocity of the reaction, because initially there will be enzyme will more and more enzyme will be free of the substrate. As the reaction progress, more number of substrate will be bound with the enzyme, and therefore the reaction rate will increase.
Very good. The answer is correct. There will be no change in the free energy because it is not changing, as I have already shown you in the last slide that where I showed this landscape. It is not changing the free energy of reactants or product, but it is lowering down the activation energy. And also uh, because as you mentioned that the enzymes is present in this reaction system, and this too will like initially when the enzyme is present, the substrate can bind much more easily, and because of the substrate concentration is more lower than the km, like much greater than the km. In that case, the substrate, the initial velocity will increase. Okay, so the option A is correct. Now the next question: enzyme catalyze a reaction at a velocity of 20 micromole per minute when the concentration of substrate is 0.01 mole. The Km for this substrate is this one. Assuming that Maclaurin-Menten kinetics are followed, what will the reaction velocity when concentration of S is 1 into 10 raised to power minus 5 molar, and what will be the concentration of the, like, what will be the reaction velocity when the concentration of reactant is 1 into 10 raised to minus 6 molar. You solve this question and then try to answer. And then I will like explain this question how to attempt this. I will give you 2 minutes. In first case, what will be the answer? When reaction velocity is when the substrate concentration is 10 raised to minus 5 molar, what will be the reaction velocity? It is very straightforward. The first one is very straightforward. Second one you need to calculate. Any answer? Anyone is able to solve the question? Okay, let me explain. So here the question is, like, in the first statement itself, they have given the enzyme catalyzes a reaction velocity. You have a reaction velocity V at like 20 micromole per minute. This is the reaction rate when the concentration of substrate is 0.01 molar. Now in the question itself, they have given the Km is equal to 1 is to 10 raised to minus 5 molar. Right? Now, as in the beginning of the like interaction, I told that when the substrate concentration is much more larger than the Km, then at that time V will be equal to Vmax. Right? That is the assumption of Michaelis-Menten kinetics. Concentration much more larger than the Km. The reaction will, this enzyme catalysis will occur as the 0th order kinetics, and at that time the reaction rate will not depend on the substrate concentration. The reaction velocity will not depend on the substrate concentration. It will be independent, and the velocity will be at its maximum, Vmax. Right. So thereby this reaction velocity that you have given, it is the Vmax. So Vmax will be equal to V 20 micromole per minute. And this analogy we get from the curve. This is your Km. Okay. Now it is given that your at the higher concentration, means much higher concentration of substrate, your reaction velocity, this reaction velocity is given at the Vmax. So means V is equal to Vmax. Now Vmax is equal to 20 micromole per minute. Now can somebody tell me what will be the Km? Km is nothing but the substrate concentration at which Km is the substrate concentration at which reaction velocity is half of its maximum, right? Vmax by 2. Okay. So it is given that Km is equal to this. Now, in the first half, they have asked this, what will be the reaction velocity at the Km value? Because Km is the same, right? 1 is to 10 raised to 1 into 10 raised to power minus 5. Okay, which means the velocity at this Km will be Vmax by 2, means 20 micromole per minute divided by 2. That means 10 micromole per minute. So 10 micromole. Now you can have two answers correct. Now coming more further. Now in the second part, they are changing the substrate concentration. Now substrate concentration is 1 is to 10 raised to power minus 6 molar. Okay. And your Km is given as 1 into 10 raised to power minus 5 molar. So your initial velocity of the reaction will be V is equal to Vmax into S divided by Km plus S by the expression of Michaelis-Menten kinetics. As it is in the question itself, they are saying the Michaelis-Menten kinetics are followed. So Vmax into 20 micromole per minute into your substrate concentration is given as 10 raised to minus 6 molar divided by. Now Km can also be represented here. What will be the representation? This is 0.1 into 10 raised to power minus 6, right? This will be the 10 micromolar. This is 1 micromolar, right? Substrate concentration is given here 10 raised to minus 6. This means 1 micromole plus 0.1 micromole. Okay, Km plus S. Now 20 micromolar means 20 into 10 raised to minus 6 divided by 1.1. That means 1.8 micromolar per minute. Right. So your option A was correct here. Is it okay?
Yes, sir.
Okay. Now the next question is, which of the following statement is true about the region of the graph below where S is less than Km? This is Vmax. This is your Km. Now, what will be the case? For this part of the graph, E greater than S. When S is less than Km, the initial rate is equal to the catalytic efficiency multiplied by the free enzyme of the substrate concentration. Or when the substrate concentration is much lower than the Km, the rate is zero order and with respect to S. This region where the S substrate concentration is much lower than the Km allows the determination of the Km. So which is the correct statement here? So which part is it talking about? Substrate concentration is much lower than the Km. Whether it is talking about the first part or the second part. Which part? Which part? First or second? Which part this question is talking about? Substrate concentration is much lower than the Km. First part or second part? Which part?
First part.
First part. So in first part, this reaction velocity is first order or zero order?
So zero order.
Zero order. What happens in zero order? Zero order is where the reaction velocity does not depend on the substrate concentration. Zero order is the second part. First part is the first order because it has the slope, right? And slope arises due to initial velocity of the reaction Vmax into S by Km plus S. So in the first part, when the substrate concentration is much lower than the Km, the reaction will persist as the first order kinetics and this Maclaurin-Menten kinetics will hold. But at the substrate concentration, when the substrate concentration is much lower than the Km, in this part, the Maclaurin-Menten kinetics will not hold. It will break. It will break at the substrate concentration much greater than the Km. So there it will follow the 0th order. Means the substrate velocity is not depending on the substrate concentration. So it will hold the first part. That is why the option B is correct. When the so it is following that initial rate is equal to the catalytic efficiency. Catalytic efficiency is kcat into Vm, which is Vmax. Catalytic efficiency multiplied by the free enzyme and the substrate concentration. Is it clear? This is wrong. This holds when the substrate concentration is much greater than the Km. And similarly, this is also Maclaurin-Menten kinetics cannot give you the Km value. For determining the Km value and Vmax value, you need to plot the Lineweaver plot, which is also double reciprocal plot, right? For getting the Km value, you need to plot the double reciprocal plot. It does not give you the, so all three options are incorrect. Is it okay? Now the next question. Maclaurin-Menten assumed that overall reaction of the enzyme catalyzed reaction could be written as this and this. Using this expression, the rate of breakdown of the enzyme substrate complex can be described by the expression which one? Rate of breakdown of the enzyme substrate complex means reaction is going either in the forward direction or in the backward direction. So what will be the rate expression? Option A, option B, option C, or option D?
Option B.
Option B. Okay, very good. Option B is correct. Why? Because if you develop the expression Forward direction is K1, reverse direction is minus K1. ES and dissociation of enzyme substrate complex into the enzyme and product is K2. Now you are talking about the enzyme substrate complex dissociation breakdown. So breakdown can happen in the backward direction also, and it can happen in the forward direction also. So the rate of the background, rate of the ES background will be minus K1. For backward direction, ES will be the reactant, right? So minus K1 into ES plus K2, and again for the K2 also ES will be the reactant. So K2 plus K2 into ES. So option B is correct. Is it clear? However, if you are asked to write down the formation of product dP by dt, what will be the dP by dt? Can somebody tell me the dP by dt? Formation of product, what will be the rate of formation of product? Among these four, which will be the rate of the product formation? Among these four, based on the based on how I did this one, can somebody tell me what will be the rate of product formation?
K2ES.
K2ES, very good. For product formation, ES will be the reactant and K2 is the only way the product can be formed. But for the breakdown of the ES complex, this can be done into the two different ways. That is why these were the addition of these two. But in the product formation, the rate will be the K2 into ES. Rate into reactant concentration. Okay. And what will be the rate of substrate consumption? What will be the rate of substrate consumption? Rate of substrate consumption will be in only one direction, right? K1, right? K1S minus. If you are talking about the consumption, if you are talking about the consumption, this will be a K1S. If you are talking about the formation, it will be minus K1 ES. And then if you are talking about the change in S concentration, it will be K1S. Okay, K1S. And formation, this is minus K1S because this is consumption, right? Minus K1S plus K minus 1S. K minus 1 ES. This will be the change in substrate concentration because till here it exists in the equilibrium phase. After this, when it is going towards the product formation, this rate is very rapid. I hope it is clear, right? Now let me show you some another picture, research perspective of a question. Okay, initially I talked about the lipase. Lipase is a enzyme, okay, which catalyze the formation of ester. It catalyzes the esterification reaction. It catalyzes the esterification. It catalyzes the trans-esterification, and it catalyzes the hydrolysis. It catalyzes various kind of reaction at lipases, and lipases are also used in various kind of industry, in food processing industry, in biodiesel industry, in cosmetic industry, and many more. Okay, so this is a structure, one structure of lipase, which is Candida antarctica. Candida antarctica lipase B. or in short cal. So here you will see there are different part of it. This is alpha helix 1 and this particular is the catalytic cavity. So if you zoom out, you will see this cal has this particular kind of structure. This research was done by me, and then this work was published in the Process Biochemistry Journal, where I deduced the different binding pocket. So acyl binding pocket and alcohol binding pocket. So and at the interface you will see this catalytic amino acid residue. Catalytic site is composed of serine 105, then serine 105, histidine histidine 224, and aspartic acid. Okay, so and glutamine Q and tryptophan 104. They forms a kind of a like negative bind anionic binding pocket, which stabilizes the generation of which stabilizes the formation of uh, catalytic site, this catalytic domain. Okay, so in the acyl binding pocket you will see that those molecules which have the COOR, which can have the ester or acid. Both alcohol and acid bind to this acyl binding pocket. However, alcohol binds to this alcohol binding pocket, which is the ROH. Now the product, once the both two substrate, which is alcohol ROH, RCOH, and alcohol both binds, then at the interface this particular amino acid residue play an important role in catalyzing the reaction, and finally the product is transferred to the acyl binding pocket, and from where it is released. Okay, and these all things happen in this binding pocket, this catalytic binding pocket. I'll show you the structure of this also. So this I proved using the molecular docking. In molecular docking, La, which is levulinic acid, binding to the acyl binding pocket, and these were and butanol, which is alcohol, is interacted with the interface, which is serine. Okay, then the transition state is stabilized by the all three interaction, histidine, threonine 40, and these hydrophobic binding pockets are also there. And finally, the ester is transferred to the fourth binding pocket. Not fourth, that acyl binding pocket, which is n-butyl leucinate. Okay, so there how you reduce, there how using the molecular docking you can reduce the catalytic activity of this particular kind of enzyme catalyzed reactions. Okay, I will show you that paper on the internet. You can find that paper on my Google Scholar profile. This is a process biochemistry paper. This one, mechanistic investigation of sonogenic synthesis of n-butyl leucinate. Here, using the molecular docking, if you go to the figure number here, this I had reduced. So here, this is the structure. See, in the catalytic site, you have these 5 amino acid residue. Before the beginning, like this is the reaction, enzyme, then first substrate. This is ping pong bye-bye kinetics, which is Y substrate kinetics. Okay, other than the Maclaurin-Menten model. In Maclaurin-Menten model, only one substrate is binding to the enzyme. However, in the ping pong bye-bye or ordered bye-bye kinetics, 2 substrate, 2 products you will see. So enzyme is there, then first substrate will come and bind to it. It will make a conformational changes in the enzyme, and the first product will release. Now the second substrate, now the enzyme is transformed intermediately, which is important for binding of the second substrate. The second substrate B will come and bind, and then finally the product will release, and the enzyme is transformed to its native state. This is what is represented here. This is the catalytic side of Candida antarctica lipase B, which is composed of serine 105, glutamine 157, threonine 40, histidine 224, and aspartic acid 187. Now the first substrate, which is levulinic acid, is carbolic acid. Now it is coming and binding, and it makes the first transition state. Now there is a specific rearrangement happening, and this is docked there. Now the first product, which is water will be released due to the rearrangement of the bonds, and then this is the transformed enzyme complex. This is the enzyme substrate complex, first enzyme substrate complex. Now it is transformed enzyme E star. Now the second substrate will come and bind to this particular modified enzyme, and then finally this will release the second product, which is the main product and butyl unit, and finally you will get the your native state. This is what we deduced using the molecular docking studies, and then we also deduced that it is inhibiting the first product is inhibit like for second substrate, which is alcohol. Alcohol is inhibitory using competitive inhibition. It is binding directly to the enzyme. Okay, and similarly the first product, which is water, also inhibits at the first site. Okay, so this paper you can refer, and we have developed the model for ping pong by kinetic operation for this particular kind of system, and then we modeled, and then we checked the different kinetic parameters. Ka for like acid binding, for Michaelis-Menten kinetics for B, for alcohol, and in absence of product, in inhibition by alcohol, inhibition by first product, and then mixed dead end product inhibition. Okay, so this is how you can like the detailed analysis is given here. Okay, you can read this paper. This is how you can proceed further to analyze the different binding pockets and the structure. So if I want to show you the structure of lipase, how does it seem? You go to the PDB database. Okay, PDB database.
So I think it is not visible to us.
Oh, whatever I showed, that is not visible to you?
Yes.
Okay. Oh, you could have said that to me before earlier. Yeah. Is it visible now? Is it visible?
Yes, sir.
Yes, now it's
PDB database entire screen visible to you? Okay. From where you could not able to see? Like
Sir,
this
which
one?
paper you
From
showed
where you were mentioning about your paper, etc.
Okay.
the paper.
Okay. I was talking about this paper. If you go to my Google Scholar page, you type in the Google Scholar, you type my name Karan Kumar, you will find this third paper, process biochemistry paper. You click on this paper, and then it will direct you to the journal paper. So in this paper, what we showed that the production of N-butyl levulinate in presence of like lipase enzyme. Lipase enzyme is uh, like enzyme which catalyze the esterification reaction. So here the two substrate were levulinic acid and butanol, the two substrate, and finally you get the product N-butyl levulinate, which is ester, and water as the co-product. Okay, and this is because there are two substrate and two products, so it is following the ping pong bye-bye kinetics that we proved using the molecular docking analysis. So this is how it is done. Right here I have showed that in the active site there are 5 different amino acid. Okay, the active site amino acid residue are serine 105, histidine 224, and aspartic acid 187. And these two, glutamine 157 and threonine 40, act as an anionic hole, which stabilizes the transition state, the charge state of transition state here. So when the first product comes, when the first substrate comes, which is levulinic acid, it makes the first transition state where the anionic hole. Here, what is the role of aspartic acid? It abstracts the histidine, hydrogen of this histidine, and creates a nucleophilic site on the serine 105. By which the aspartic acid abstract the hydrogen from this conjugation of histidine 224. Then this generates the charge on this particular nitrogen of histidine. This particular negative charge is stabilized by the abstracting the like hydrogen from this like serine 105. Serine 105, serine has the OH side, right? So this hydrogen is abstracted by this histidine nitrogen, and this creates a nucleophilic site. Now this nucleophilic site attacks on the carboxylic acid alpha carbon, and thereby it generates a this transition state. Now the negative side generated over the this particular transition state are stabilized by the glutamine 157 and threonine 140, 40, and this is how the anionic hole stabilizes this transition state. Now the again rearrangement happens, and the first product, which is water, is released due to the rearrangement. And now finally, what happens? Now your enzyme is modified. Your water is released, but the another moiety of levulinic acid is still attached to the enzyme, which is acting as a E star. Okay, which I shown here, the schematic representation. First, first substrate come, it makes the enzyme substrate complex. Then the first product is released, which leaves the enzyme as a intermediate state, modified state. Now the second substrate come, which is alcohol, and it is again making the transition, second transition state, and then you will release the second product, and your enzyme will recover. So this is how it is done right here. The first, this is the tetrahedral intermediate where the enzyme is modified. Now the second substrate butanol comes, and it again attacks on this particular site. Okay, and you release the first, you release the second product, which is the main product, and butyl levulinate, and finally your enzyme is regenerated, and again this cycle goes on. This is how enzyme catalyzes the reaction. Now let us assume when the enzyme is not present and you have only levulinic acid and alcohol in your system. The collision might not be much effective and the reaction will not be faster. This is how the enzyme takes up one substrate, make the modification, then take the second substrate and release the product. Finally, resume its original site. And after that, we also noticed that the second substrate, which is alcohol, also inhibit competitively, and the first product of the reaction also inhibit the by competitive fashion inhibits the lipase enzyme, which is water, right? So this is how we showed. And other than that, the more mechanism, the binding, we developed the model of this kinetic model, and then this is how the more in-depth analysis of the binding pocket, and then how this is related to it, which are all the amino acids are involved in the different binding, that we showed using the molecular docking. Now, if you want to check the structure, how does it look like? You check 1-TCA. 1-TCA is the PDB ID for Candida antarctica lipase B, the enzyme that I worked on. Okay, and it will pop up this structure. So this is how the enzyme look like. Structure. So these are the amino acid configuration, L, P, BG, these all total. There are 316 amino acid residue, and this is how the alpha helix is represented. If you hover anywhere, you will see which kind of amino acid it is. This is E, which is glutamic acid, then glutamine, then lysine. So if you want to see where is the active site is somewhere near to this site. So those were the histidine 224. Histidine 224 is here. Okay, histidine 224 selected this site. So here you will see histidine 224 glutamic acid 1. So this is your particular active site. Here the binding will happen, and this is how you see that you can see the different like hydrogen bonding of this water molecule. This is the water crystal water, and this is binding. This is making the hydrogen bonding with the histidine residue. Okay, this is the tryptophan 204, and somewhere near you will find the aspartic acid and serine 105. Okay, so this is how you do the with the help of molecular docking, you reduce the catalytic side. You can read my paper, and then you can, if you have any doubt, you can ask me anytime. So by this, I think like phase 1 of enzyme kinetics is over. So if you have any doubt, you can unmute yourself. You can ask anything related to the previous session and related to this session also. Or else you want to give any feedback, you can give your feedback.
So, is there any possibility like substrate of same molecule, like one
Yes.
molecule of same substrate is behaving like as a catalyst for the other molecule of the same substrate?
Yes, that is also possible. This is what is seen in hemoglobin binding, oxygen binding of hemoglobin. So here in hemoglobin they have the 4 binding site for oxygen. But when oxygen is a substrate for that particular binding site, oxygen is a substrate for hemoglobin. When one molecule of hemoglobin is binding to the one binding site, it makes the rearrangement and it allosterically activate the different active site also, so that the binding of another oxygen molecule is faster. So that is how the substrate is also activating its binding to the enzyme. So it is possible. That is what is seen in the
Okay.
hemoglobin case.
Okay, sir. Thank you, sir.
Welcome. Any other question? Anyone else? Any feedback you want to give?
Sir, one more query. Like the
Yes.
final examination of biochemistry, uh, is it include negative marking?
I don't think so. That will be declared, I guess, in the instruction of the paper. They might revise the instruction. So before attempting the question, you must read the instruction carefully.
Okay, sir.
So yeah. Anything else? Anyone?
So is there possibility that we will have a separate lecture on the topics that we have some sort of confusion? For example, in more depth, you have explained that in previously, but it will be beneficial if there will be further discussion on those topics.
Which topic?
I
If you
think
mention,
so.
I will make an arrangement for that.
I think so. The ionization of amino acids and
Okay.
those topics which contain the formulae, that portion.
Okay. Actually, I have created a WhatsApp group.
Yes,
Okay.
sir.
So if you are comfortable, you can join that WhatsApp group. The link is provided in the this one. Or else you, if somebody is not comfortable in joining the WhatsApp group, they can mail me their interesting topic. Or if they want to get a clarification on some other topic which have been already covered. So in the next live interaction session, I will take up those things before discussing any problem.
Thank you, sir.
Okay. Yeah. So this is the WhatsApp group link, and YouTube channel also. You can also comment your doubts in the YouTube video. Okay. Last yesterday's session also have been already uploaded on my YouTube channel. So if you have any other doubts related to the respective session, you can ask that in the comment box also, or paste your doubt in the discussion forum. Okay. So there are multiple ways to clarify your doubt, and we are here to clarify your doubt only. So we will be happy to do that. Any other query? So you one thing you have mentioned that that is like pK, amino acid, pi, and all isoelectric point,
Yes, sir.
right?
Yes, sir.
So is there any other thing
Yes, sir.
you
Please
want to?
clarify.
Sure. I will take that in the next session. So you please drop the comment, or you please mail that to me so that I might recall in the next session. Or you in the beginning of the session itself you mentioned that sir, last time we were asking for that. So I will definitely take that doubt. Okay. Okay. So is if there are no further doubt, no further comments, so I will end the session now. Thank you for joining, and I hope from
Great session
yes,
today. Thank you.
thank you, Abhilasa.
It's always for taking your class. It's great experience.
Thank you so much. Thank you for this feedback. You can also give your feedback in the feedback form that is available in
Yes,
the
yes.
course website. So there you can, especially in the remarks, you can mention that this particular TA was like clarifying the doubt very easily. So you can
Yes,
mention your
yes.
feedback there also. Thank you so much, Avilasa.
Okay, so thank you, sir.
Thank you, sir.
Thank you. Okay, we from the next class onwards, the Friday will be the usual time, 6 to 8 p.m. So that will be the usual. We will be following the usual thing. Thank you so much
Sir,
for joining.
so one request, we are not getting the updates from other TAs.